So we're gonna go through and then we'll apply practically to suppose you know the actual distribution, say it's Gaussian of a current source, and you wanted the distribution of power, probability density function for power in a resistor, for instance. But first, we'll do this. I'm going to say that I have, it'll be a Gaussian current, Gaussian distribution of x, random variable x. So that means f of x is going to be equal to 1 over the square root of 2 pi, and then sigma x exp to the minus quantity x minus x bar squared over 2 sigma squared as such. And I think everybody can follow me on this one. We're going to go through this. I'm going to do something right now. I'm going to assume x bar is 0. Doesn't have to be, but it'll make the problem a little easier to track. And in that case, if x bar is 0, I have this distribution. Doesn't have to be, all right? Now I'm going to create a second, you obviously see this is Gaussian. Everybody with me? Now I'm going to create a second variable, and that is y is equal to x squared. Now this is standard, by the way. This type of thing goes on all the time when I deal with radar work and everything like this. You're going to get functions. We know distributions of certain things, but we're going to have functional forms of other things that will be squared powers and exponential powers. And you need the statistics about these two. So if we take a look at this, first, when we graph this, if this is x and this is y, you can see that what I really have is something where y can never be negative, and x can be negative, right? So I'm saying here x can be negative. You'll notice I made the mean 0 for an obvious reason, because this parabola is a lot easier to track than something where it would be skewed off with a different 0. You all with me on this, class? But the principle is the same. So I have that. So I want now my f of y. So I want an f of y of y. Well, I'm going to show you how I think about this. For instance, I look at this, and if I say if x can be from minus x to positive x right here, that means y itself has a limit from some value here, which is going to be x squared to 0. You all follow me on this, class? So the range is strictly positive. If everybody follows me, I'm not writing all the formulas down. I'm just talking I guess in general terms. But we know the standard way to do this, to get a probability density function, if we have a probability density function of x, and we have an f of x, and then we have a function y that's a function of x, then we can get it this way. It's fy dy is equal to, it would be times dy is equal to f of x times x dx. But I'm going to take this down here, and I'm going to put dy dx here. The reason I'm doing it, I'm trying to make sure that you see, normally it would be what? Dx here, if I divide everything by dy first, and then take the dx down here, you get this. Now this is true, but I want to show you something about this that's important. This dy dx will have 2 points where the magnitude of that slope will be the same. One will be here, and the other here. Can you all follow me? Everybody with me? This is, you'll see this if you do it. Did you read this in the book at all? Anybody? Or in the chapter? This is in, I'm sure it's in Chan, but it is in Cooper and McGillen. And because it's a very practical example of something. If this was just like y equaled x cubed, which is an odd function, it would be different. Then you wouldn't have to worry about that second derivative. Or I should say the possibility of 2 points having the same magnitude as derivative. So if I take a look at this, and I take a look at this equation, that means dy dx here is just going to be 2x by itself. Do you all follow me? Okay, so now I come down here, and I say, and I should erase dy here. This is going to be f of x, this is important what I'm about to show you, over dy dx, which is 2x, right? Now, f of y cannot be a function of x. I think we all agree with that, right? So what I'm going to do now is, I know x itself, if I take the square root of both sides, I have square root of y here would be equal to x, right? But this would be plus or minus. There are two possible roots to that. You all agree with that, class? That's where we're going to get a little bit of complication. I'll try to explain. So here, now I have f of x. That's f of x, but you simply substitute in x is equal to square root of y. I'm going to write this down, so I'm going to have 1 over square root of 2 pi sigma x. This way we get one that's got a little more ink left. And then I'm going to have exp of minus, now normally it's minus x squared over 2 sigma squared, but x squared is y. Can you all see that? So here is going to be y over 2 sigma x squared. And then when you divide this, the whole thing's divided by 2x, or it's going to be 2 times the square root of y. Well, actually, I can do it like this. I can just put this right here. So it's going to be sigma x and then 2 square root of y here. Now, oh boy, let me try this one more time. Now that would be true for one of the possible roots of this, positive x. Because there's a negative root, now follow me on this. Are you with me on this, class? There's a negative root too. Basically, this is positive, this would be negative, and the solution is plus or minus the square root of 5. Now you have to add this second point, which is going to be plus, and that's where it would be there. It would be exp to the minus, and it will be positive y over 2 sigma x squared. And you get this. In the book, he shows this, and I want to give you the page number so you can actually look at this. You can really just get rid of that 2 business. This isn't on the quiz today, but you will see this, and this is a good problem to start with. Yeah, actually, I should say this. Normally what you would do, since this is going to be x squared and x squared here, you would put x is equal to the minus the square root of y. Well, when you square it, you get the same thing. You all follow me, class? Minus y, minus the square root of y, squared is just y, and plus the square root of y, squared is just y. So it's really just going to be y here. And the reason I'm doing this is this will be y, and this will be y. Here's the real reason. Can everybody see these are identical? So what actually happens is this. Get rid of one of them and just multiply by 2 or get rid of that. And this would be, that's a y in there, not much of a y, but it is a y. That is the distribution function. Now, obviously, that isn't Gaussian. I got a square root of y right there in the denominator. But it is the proper distribution. Now, the obvious problem with using this distribution function, if you want moments of y, or you want the average value or anything, is you would have to do that integration. That is not the standard Gaussian integration for the normal distribution. So rather than messing with that, and you could, rather than messing with that to do integrations to find moments or the probability of y between point A and point B, what I would recommend you do is stick with x, that if y is between these two values, what's the values of x? That's where I'm going next. Can you follow the rational thought on this one, class? This distribution's a pain in the butt to work with. It is correct if you want to get numerical values in reasonable times. However, a better way to do it, if you want y between two values, look at what the range of x would be for those same values. Can everybody follow me in this class? That's the rational thought. So now we're going to do a problem where it's power and a resistor. And by the way, this is a very good problem because it really shows you how you would go about solving a problem that had Gaussian information about some distribution, but what was asked didn't have to do with that variable Gaussian information pertaining to. Has anybody else in here been sick at all? You were sick when?
I just have like a cold.
You got a cold now?
Not now, but like a day or two ago. Kind of have one.
You got one now? It's been with me this whole week. It's irritating the crap out of me. It's much better now. It's waning away, but not fast enough. So here's what one of the problems that's in Cooper and McKillen, but it's the book I put up there. I believe there's a problem, I can't be sure, like this in Chan's book. The thing about Chan, he'll add an average value. He'll make sure he gets it complicated as crap when what you're really trying to do is just see the essence of how to go about it. So here's the problem. We're going to have a current distribution, f of I, and it's going to be Gaussian. So this is going to be Gaussian. It's equal to 1 over the square root of 2 pi, and then the sigma here is the current distribution standard deviation, exp minus I squared over 2 sigma I squared. I made sure the mean is 0 this one. I'm sure Chan wouldn't on purpose to make the math a little more complicated, a lot more complicated. And here's the thing. So this is a current, or better yet, instead of a current, let me make it a voltage. And the reason I think about that, because when you get sources, you usually get a voltage source, not a current source, right? Voltage sources, and Gaussian noise on voltage sources is very, very common. It's called noise, or Gaussian distribution. So I'm going to make this a voltage to make it a little more, let's say, appropriate. And what I should say is a lot of times, when you have digital circuits, you're going to have, quote, ones or zeros. Is going to be the state. A 1 would correspond to like 5 volts, a 0 to 0 volts. But there's always noise superimposed on that. So there would be Gaussian noise superimposed on that. And then that means the average value of either the 0 state or the 1 state, you would take the value 5 or the value 0 and you would add that onto it. And then to figure out the probability of an event occurring as it's defined, you would have to use that 5 or 0 as the mean value. Y'all follow me on this one? So back to this thing. This is the voltage. So here I'm going to take the voltage plus to minus. And this is going to be a voltage here, but it's got a Gaussian distribution. And now I'm going to, this is a problem in the book. I forgot which one it is. It is a problem. And I'm going to say that here I have a resistor. Which problem is it? I want to say they put 2 ohms here, and for this one it's 0 mean, but the standard deviation I think is 4 volts. Let's see if I can figure that out. Oh, this is exercise 2-6.1. Wow. somebody. So now, right here at the top, that's what they're asking for. So we've got this, it's zero mean, and now they want some information about it. What's the thing that they want? I remember. Huh?
Could you read this? My voice is kind of.
Oh yeah, I'm sorry.
No,
Because I know the feeling.
The approximate probability that power dissipated in the resistance is between 9.9 watts and 10.1 watts.
Okay, I'm gonna use W for the symbol for power, because it's used in the text. And so a power greater than, is it 9.9?
But yeah, between
And
9.9.
less than 10.1?
Yes.
Now, here's the mistake you would make. On a test, I could imagine people would say, well, I know that's the statistics of the voltage, but I want the statistics of the power. And here, the power would be equal to V squared over R. First, does everybody agree with that? All right, which means also, V itself would be equal to the square root of the power times R. Now, I would want the statistics of W. I could ask you for the density function for W. That would be legit. And for this one in particular, because it's power, you would have to add that. Remember, you'd have to take the F of W on one side of the derivative and multiply it by 2, because it's one of these things where it's an even function. Do y'all follow me? That's what I just did. But a better way to do this is just use this. You with me? Work this problem with me on your calculators as I set it up. So when I take a look at this, 9.9 to 10, right? I'm going to find the voltage, and I want you to be attentive here. I'm going to find the voltage that this would correspond to. You'll notice that voltage has both negative and positive values. So for this one, for a power right here, I'll call it equal to 9.9. That's equal to V, I'll call it V low squared over R. It's 2 ohms. So that means the voltage at the lower end of this, at 9.9, would be equal to the square root of 2, because R is 2. I think I put that down. Yeah, R is 2 times 9.9. I want to get that from you. And the upper voltage would be equal to square root of 2 times 10.1. These are going to be close. But I did this on MathCAD last night, I believe. And you all agree with that? With me? I'll call it V low and V, I call it V high, H, right? Now, here's the thing, and you gotta make sure you've got this down. If we look at the voltage, remember this is Gaussian distribution. These are negative values, these are positive values. The actual power W is V squared over R. We know the curve is gonna look like this, right? So for the positive voltage from whatever this is, V low to V high, the area under that curve, you might say, or I'm trying to show you the appropriate area. Y'all with me? The voltage between here and here would correspond to the power between there and there. And likewise, this is a density function, between minus V low and minus V high, this would be the area involved. Can you all follow me, at least my thoughts on this? Now that isn't the probability density function. I just want to say that that would be the areas or the ranges you concern yourself with. Now I'm going to make this statement, and I hope you can all see. Can you all see how this is an absolutely even function here? Everybody? If you drew, just cut this thing up here and folded that over here, you would overlay. It's an even function. So if I take twice the probability of this range, that should give me the right value. Do you agree with this? Let's see for this. So how do I get this? Anybody give me a value for this?
4.45.
For the top one, 4.45, and the lower one?
4.49.
Man, not much difference. Probably need a few more decimal places, but that's the idea. With me? So what's the probability of the Gaussian distribution between here and here times 2 it's gonna be what? I mean, the way I'm gonna do it is this right here, and I call it, it would be the probability, now listen, I'm gonna use the cumulative distribution function. You have the ability to show the limits, right? For yours, it's easy because you just put in this as, or this is the lower, this is the upper, put in the standard deviation and well up, but you have to multiply by 2, right? Isn't that right, class? The way I did it was, I'll take the upper limit, which is gonna be, I use this cumulative sign, so I'll call it f of I, and here, I'm not I, v, pardon me. And here it's gonna be a 4.49, now that's the cumulative, and I could put a 0 mean in there, and I could put the standard deviation, but I'm implying that they're there. Remember this thing? And then I'd subtract off the f of, for the voltage of 4.45. That would be on one side, V positive, I multiply by 2, and that should be the value. Can somebody go ahead and do this for me? If you want to, just put the limits down the normal distribution from the lower to the upper with a mean of 0 and a standard deviation of 4. Take that value, multiply by 2, what do you get?
I got 0.00428, but I don't know.
Did you multiply by 2?
That's what I said.
Point oh what?
00428.
I'll tell you what I got 4.775 times 10 to the minus third. Did you get that? Now I'm going to tell you one thing. I have more digits.
Yeah, I was gonna say the book has 004.8, so yours sounds close.
Yeah, and that's what I'm talking about, because look at the difference in these two. It's in the third significant figure. You probably need a few more. Your method is exactly right, but these are not exactly
Would
right.
you lose points on that?
No, but
Okay.
I mean, it depends how bad it is. If you put this is 4 and this is 4, yeah, you're gonna lose. All right, 4.4, 4.4, probably. 4.45, yeah, I'll probably wink at that one, but try to appreciate from my perspective, I'm trying to get you to be accurate. That's my motive here, not to be sloppy. All right, go with me? And that should be, it's one of the 3 answers.
Yeah, so, yeah, that's right.
All right, now what does he ask me? Make sure you can understand this problem and do it, by the way, because this problem exemplifies the kind of questions that come in. The next section, let me just give you everybody perspective. We're going to be talking about distributions that are based on Gaussian but are non-Gaussian. In other words, we're going to be talking about something called a Rayleigh distribution, named for Sir Rayleigh. And we're going to talk about, we're not going to talk about Maxwell-Boltzmann, but we're going to talk about some distributions that are derived from this. This one, you just use Gaussian. Don't mess around with the power. You with me? It's much easier, but go ahead.
The probability that the power dissipated in the resistor is greater than 25 watts.
All right, so how would you do that? They want the probability that the power is greater than 25 watts. Good question. I could see myself asking that. What is that really asking?
We should just do what we basically just did, but then your integral range would just be from 25 to infinity.
Times 2.
Oh,
All right, now listen, that's the dangerous thing about this. Remember, when we take a look at this V right here has plus or minus values. Go with me, it's a square root. I mean, basically what you're going to get here is if I say that, what is it, 25 watts is the limit, and we want to be above that, is equal to V squared over R, and R is 2. That means V here is the square root of 50, whatever that is. Do you agree with that, class? So that's a square root of 50. But if you look at this and think about, now I'm going to show you the density function for f of V versus V, it's this, right? Something like this, it's a bell curve, and here's 20, or I should say, here is square root of 50 positive, and then down here, it's minus the square root of 50. Can you all see this, class? Now we want above 50, right? That's this area, which is identical to this area. You have to integrate, technically you'd integrate from minus infinity to this point, then you would add from this point to infinity, because those voltages correspond to a power greater than 25 watts. Clear on that? What you actually said, I'm so glad you did, was it's just an angle from positive square root 50 to infinity, which would be 1/2 the actual correct answer. Everybody with me on this? And out of curiosity, when I do that, this is part A, right here. So this one is going to be what? It's going to be 2 times, and it's really the probability it's greater than 25, or 2 times, for my way of doing it, 1 minus f, in this case, I'm calling it f of v of square root of 50, right, comma 0, comma, standard deviation of what is it, a 4, right, a 4, because I'm going to take, 1 would be the probability it's between minus infinity and infinity. If I want the probability it's greater than 50, I take that minus this, because this is the cumulative distribution function from minus infinity to square root 50. I have to multiply by 2. What is that? Did you do it on your calculators? Make sure you can do this correctly, because you're going to get a problem that you're going to need to do these kind of calculations.
I mean, I got .077.
What did he have?
I think .077. Is that
Sounds
right?
like we might be right. Did anybody else get that?
I didn't do the 1 minus though.
No, but you have the ability to put
Oh,
the limits.
yeah.
I don't. I mean, I probably do, but I don't use that. Because he talks about this cumulative distribution function a ton, so I'm going to use it. That's in the back of the book, by the way. All right. He normalizes it. He has the capital 5 function, which is fine, but I prefer I want you to get used to using your calculators. That's why you paid money for them. And that's what you're really going to use in the real world. I doubt you'd look this up on tables. I doubt very much. Everybody has a calculator, can do these, right? For sure? If you don't, now is the time to speak up, and we'll get somebody to help you. Okay? What's the third part?
The probability that the power dissipated in the resistor is less than or equal to 10.
Okay, that last part's pretty obvious, but how would you do it? Probability of what? The power W is less than or equal to 10 corresponds to what? Well, power is V squared over R, right? Square root of WR is the V positive. Agree with that? But it has to be minus, correct? So really, less than or equal to 10 is what? It's this range. If V here is going to be minus 10, positive 10, remember, that it's less or equal to 10 watts, right? So this actually is not 10, it's what? It's going to be the square root of 10 times 2. This is minus the square root of 10 times 2. And this area would be it, right? Do you agree with that? This is the probability density function for V. We're going from the lower to the upper limit. Do you agree with this, class? No. Can you see it? I gotta make sure. Everybody see this one? All right, well, that's really gonna be 2 times this area, right? Agree? Now, you can do it any way you want. How are you gonna do it? Or you can take F of V, F, capital F of V, where that would be, the V would be square root of 20, and then subtract from it F of minus the square root of 20. Do you agree with that? How many do? Now, how is yours going to do it?
So would you use those as your bounds then?
Yeah, lower bound, because it's less than, right? The power's less than. Well, that voltage corresponds to the threshold. Anything above it is greater than, right? So anything below it, that's from here to here, but also from here to here, right? So what I did, I think, remember I'm using a cumulative distribution function. I just am going to say it's F of V here of the square root of 20, right, comma 0 standard deviation. minus f of v of minus the square root of 20, comma zeros, and I'll get the right answer, I believe. What did you get? Do it on calculators. Make sure you can do these things. There's tons of mistakes that are made.
Oh, you don't multiply this one by 2? Oh, yeah, because you're
You got the upper and lower ranges, right?
0.736, which is what he has to.
What did you get?
0.7364.
Check it and see if you get that right.
That's it.
Everybody get that? Make sure you do. I'm really trying to make sure you know how to use your calculator. We're missing somebody today. That guy, there's a young man that sits in front of you.
Yes, sir, I think so.
Anybody got his phone number you can text him?
I texted him.
You did?
Yeah, I did.
Did he respond?
Yeah, I think he's on the way. He said he woke up late.
Well, I wish I did. You got that? I got it before 6 today. Anyway. Yeah, I know. I feel the same way. I don't know. What is that? It's like something got me. Anyway, do you get it, everyone?
So why can't you just use the wattage values, like if we have the ability to?
Remember, if you want wattage, you want to use that, then you have to get the wattage distribution. It's not Gaussian.
Gotcha.
Remember? And that's the thing. When you get a distribution, it's not Gaussian. Now you don't have the ability to use that, all that information, the normal distribution stuff we have available. Then you would technically have to integrate that function, which is a pain in the butt. If you want, I mean, you can do it numerically, but to do it analytically can be a real trying event. I didn't even try that. Did you have a question?
Not directly about this, I was gonna ask about the one on last night.
Which one?
6-5.5, or 2-5.5.
All right, let me get to it. I'll put it over here. By the way, are these lights as bright as they do? I don't know. I'm hoping they do. It seems, I don't know, just a little bit darker, but I can't really tell if it bulbs down. Anyway, which problem is it?
2-5.5.
5.5, go ahead.
It's really, it's long.
Well, hold on.
Like, I'll read.
He's got the book. Can you go to the problems in the back? Go other way, other way. Right in the back of the chapter. Keep turning. He'll read it.
You know, pages on.
What page is it on? Can you see?
I can't see a page. I just have the screenshot.
Hold on. It's not. These are uniform distributions.
Oh, perfect.
Two.
You just flip right to it.
Lucky me. 2-5.5. A common method to detecting a signal presence of noises to establish a threshold. I'll read myself.
Might be better.
A threshold. Profound thoughts. Yeah. The presence of noise established. Compare the value of any observation with the threshold. Basically, he's saying he's setting something above a point, it's 1, below a point, it's 0 kind of thing. If the threshold is exceeded, it is decided the signal is present. Sometimes, of course, there's a false alarm. This is a radar problem. Usually, it is desired to make the probability of false alarm very small. Yeah. At the same time, we would like any observation that does not contain the signal plus noise to exceed that does not contain the signal plus noise to exceed the threshold with a large probability. This probability detection should be as close to 1 as possible. Suppose we have a Gaussian noise, with a 0 mean and variance of 1, and we set the threshold as 5. So let me give you the shot on this one. talking about, we've got a voltage distribution, and it's Gaussian. I think it's implied zero mean. Did I read that right? So this noise is going to be superimposed on a signal, wouldn't it? And it looks like this. And the actual, what is it, the mean value, well, the V bar is 0, and the standard deviation is a standard deviation variance. A variance of 1, which is the same thing as standard. So this is 1, which means sigma squared of V is 1. And they're going to set the threshold at 5. Right, so that means V threshold equals 5. And then they say, find the probability of a false alarm. Okay, so if you look at the essence of this thing, here's 5 volts, right? This is 0 volts. I'm showing voltage. This is the density function. So I want this. Do y'all agree with that? Now that's got to be small. You're 5 standard deviations away. We might have to use Q of A. Do you remember that function I said that was the approximation? Did you try this? I wanted to ask you this.
Yeah.
Did you get an answer for this?
I got an answer, but I thought it was wrong. That's why I was.
Did you look at the answers in the manual?
No. My calculator got the wrong one, and then I tried the formula from class, but I think I wrote it down wrong, because I also.
It's in the text, but let me first, y'all have calculus, right? I want you to try this from 5 to infinity. So what I want you to do is find out, this would be the probability of V greater than 5 here, is really going to be 1 minus, you're going to find out, this is extremely small. 1 minus F of V, and the value is 5, mean is 0, standard deviation is 1. Now this is going to be approximately 0, you're going to find out. Actually, yours might have the right answer, it might default to that formula. If you integrate from 5 to infinity, what do you get?
0.287 times 10 to the negative 6. Or
0.287 times 10 to the minus 6. Is that right? Can anybody take a look at the answer? I don't have my slides.
I think that is right.
I'm good. I think that is right.
That is right? All right, that's small. I mean, I would have thought you need the other formula, Q of A was 1 minus 1 over 2a squared times all that crap. Remember this one? I would give that to you if I expected it. But I guess your calculus, yours probably defaults to that formula when it gets to a certain point. Did you get it?
Yeah, I got the right answer.
All right, and that answer's right. So what's the next part? Let's see. This is a good problem. If a signal of 8 volts is observed in the presence of noise, if a signal of 8 volts is observed in the presence of noise, find the probability of detection. Well, this is not worded the way I like. He should say, he meant to say there's a signal there. There is a signal, but what's the probability of detecting the signal if the threshold is set to probably 5 volts? I'm going to say a common method for detecting a signal present of stuff. Sometimes, of course, noise alone will exceed the threshold, and this is known as a false alarm. Usually, is desired to make the probability of false alarm very small. At the same time, we would like any observation that does contain a signal plus noise to exceed the threshold with a large probability. Okay. Let me see if I can try to explain this correctly. So he's gonna say we observe 8 volts. And basically, we got 8 volts here. Now, we don't know if 8 volts is actually a signal or not, all right, because there's noise superimposed on the signal. So what it really amounts to is, where is the signal's value if it's being set? Is it 5 volts, 4 volts, 3 volts, and so forth? So for this one, if you look at this at 8 volts, the probability of that being a false alarm would be the integral from 8 to infinity of the density function. Do you agree with that? That's extremely small, I promise you that. I don't know if he does that in the solutions method. 1 minus that would be the actual, because that's so small, the likelihood of it being a signal. And you really should give the thresholds, what the threshold is, because when you superimpose noise on top of that, then the problem kind of makes sense. I'm just curious about one thing for this one. Does he have any assumed signal value in that answers, in the solutions? I don't know. Does he?
I don't know.
I didn't think so.
Does he have 1 minus probability of the signal exceeding 8 volts?
I believe so,
Yes.
but
All right, I don't like that, because what normally happens is if you got 8 volts here, you're way out here. The area under this curve has got to be just about 0, right? So for it to be 8 volts, if you take the probability of just the noise getting over 8 volts, 1 minus that is the probability of signals there, if that makes sense to everybody. And that's got to be super. I mean, that has to be like 99.99999%. Is that the answer he has? But what is, I gotta ask this. So what is the probability of a voltage in excess of 8 volts? This has got to be 10 to the minus 10th, or
I
minus
got-
11th at least.
I got 6.28 times 10 to the negative 16.
Is that anybody else?
That's the area.
Say that again.
6.28 times 10 to the negative 16.
All right, so your calculator is defaulting to that Q of A thing, that approximation. There's no way you can do that with the standard Gaussian integration calculator. That's almost nothing. And so 1 minus that would be the right answer, which is just about 1. And I don't know what he put down for a percentage, but it's got to be 99.9999999. Is that right?
The answer is 0.9987.
1 minus that?
No.
That's
That's
not
what it has
exactly,
to-
that's not exactly what he does, though.
So I think he's saying the threshold is still 5.
Oh. All right. Now, it didn't come across that way in that problem statement. If the threshold is 5, if there is a signal, but it wasn't explicit, was it, in the statement that I just read? I don't think so. He said exceeds 5. He didn't say 5 was the signals. He just said exceeds. So if it exceeds 5, then what you've got is this. Try to listen to me now. Now you've got 5 volts here, and you simply superimpose. This is what he's trying to do, the Gaussian distribution on that, all right? Now, if you take a look at this, here's 8 volts, right? I want to make sure I get this across to everybody. You with me on this, class? So what we're really talking about is the area above that, right? Do you agree with that? That would be the probability that the actual, and I'm trying to explain this, that if the signal was present and there was noise, that it would exceed that point. So signal present, the average value would be 5 now, right? So that value right there, and you can do this in your calculator, you can just say, if you're taking the lower limit, I'm not sure how you're doing this, the lower limit would be 8, upper limit would be infinity, the mean value is 5, standard deviation, or sorry, is 1, isn't it for this one? Pardon me?
Yes.
1. That would be the probability it's greater than that. If you can do your limit from 8 to infinity. When you do that, you're gonna get a value that's more reasonable, because this is only what? That's only a value of 3 away from the actual mean value, correct, class? What do you get for that?
0.00135.
0.00135. All right, so that means the probability, and he has it of a signal being present. Is that right? Was that the wording?
It says if a signal having a value of 8 volts.
Probability detection.
So that would mean the probability of detection, if it's 8 volts, would be 1 minus that. This is, so 1 minus that is what? I don't know. 1 minus 1.35 times 10 to the minus third. This is very, very close to 1, but it's not 10 to the minus 16. What do you get?
It's 0.99865.
0.99865. Is that what he has?
Yeah.
All right, that's the way he's doing it. I'm gonna spend more time on that later, but these are something where noise is superimposed on a signal, and you need the probability of the signal being there or not being there. And it's really, there's a couple of things. There's 4 things that can happen, and this is from radar, I know it's right. If you have a measurement of it can be no target, I call it. No target, noise. All right, that would be a false alarm. It can be, and this is something, you can have something where you have a target present, or I should say, no target, and you detect a target, that's a false alarm. No target and you don't detect the target, that's correct, that's valid. Then you can have target present, but you don't detect it. That's a lack of detection, that's bad. We put an X there, we got 2 X's out of 3. Then target present, we detect target. That's correct. We get 2 out of 4. I mean, basically for every possibility, the event, either a signal or a target, can be there, and you can either detect it or not detect it. And all that is based on statistics. What happens, we're going to see this, when you have multiple times that you're interrogating an area. I mean, basically, I'm talking about a target being there. I send out a signal, get it back. I go through my algorithm, it's not there. Send it out, get it back, not there. Send it out, get it back, it's there. Now I have to look at the statistics of like 4 detections in N attempts. What does that tell me? The probability the target's really there. This is where statistics get more and more difficult to understand, because the targets themselves have different statistical distributions. They're not all Gaussian. So without getting down that road, that's where this applies to my world that I live in. And you will see it apply to your world too, depending on what it is. If you're building solid state circuits, VLSI and stuff like this, you'll find any kind of digital stuff. There's always going to be noise on signal lines and stuff like this, and they always try to find the probability of the circuit not doing the right state change. And that's very, very important, because it's cumulative. Think of how many transistors are on one little VLSI chip, 10,000 to 100,000. And each one of those has a probability of not functioning right. And then it comes into, then where you go from that arena is how many have to malfunction for the whole chip to give errors. And there should be some redundancy, but that's down the road, but that's where some of you will live. Okay. Last thing I'm going to do before we get to quiz. This is the Rayleigh distribution. Now, the Rayleigh distribution is extremely important. And I'll tell you why. How many here have shot a rifle or a bow and arrow at a target, or know what I'm talking about? If you aim, basically you have a circular target with rings that expand. And you'd like to know something, if you're doing this, about the probability of hitting the bullseye and how far away you are. Now, hear me on this one. This is where this really comes from. So if you have crosshairs here, there's your 0, this is X, this is Y. we're gonna make this really simple. We're gonna assume that there's some distance r away, not a function of angle in this case, but r itself is just gonna be equal to the square root of x squared plus y squared. Now it should make perfect sense. We would like r to be 0, or we would like to strike the target right where we're aiming. This is an aim point, think of it like that, with me? Now, we're gonna assume that we know, and by the way, this actually works very well, that we know that the standard deviation on the vertical axis is Gaussian, and the standard deviation on the horizontal axis is Gaussian. So listen. So that means that sigma x is equal to sigma y. Actually, sigma y skewed more because gravity causes things to bend, but it's not a big deal. This is amazing how accurate this is. And these distributions, for this one, the mean of x is the mean of y is 0. And both f of x and y have distributions. I'm only going to show you x here as 1 over the square root of 2 pi times sigma x, exp minus x squared over 2 sigma squared sigma. And what that is a probability density function that has to do with where that arrow or bullet will strike. So if you were just looking at the x-axis, an f of x, you would have something like this. The greatest chances, if you're aiming right, is hitting bullseye. Follow me? But there is a probability that you're going to be greater than some x1 here, above or below. With me? Now, when we talk about the Rayleigh distribution that comes from this is R. Now, write this down. The Rayleigh distribution itself, first of all, it works, it's proven. It has to do with the magnitude of the square. So it can never be negative. Do you follow me on this one? And R, f of R, is equal to R, that's just the radius, over sigma, but this is sigma x squared. It's not sigma, it's not the standard deviation of the measurement R. This is important. So these have to do with the Gaussian sigmas. And then it would be exp minus R squared over 2 sigma, it's either sigma x or sigma y squared. And this is true for R greater than or equal to 0. Now, I want you to know it's used all the time. And just want to make sure I'm not going to get an AU alert that a camp is somehow gone bust and I've got to get out of my parking spot. Anyway, for this, I want to, the next thing I want to tell you, so that's the density function. Now, can everybody see that density function here? If this is R, the density function FR of R is going to be, look at 0, it's 0. It starts at 0, but it's going to go way up and then asymptotically drop down. Y'all with me in this class? That is going to be the density function. It's really important to understand that. We'll talk about the mean value of this, and we'll talk about the standard deviation related to this Rayleigh distribution. But the nice thing about this, if you integrate that thing to get the density function, now I'm going to call it the cumulative density function for R, which is the integral of that, but it's from 0 to R of f of R dr. I'll put a prime there because the limits can't have the same arguments as the kernel of integration. It can't be of the same form as the kernel of integration. You're going to get 1 minus just exp to the minus R squared over 2 sigma. This is sigma x or sigma y squared. It's not sigma real. And that's true for R greater than or equal to 0. Now that's nice. It's a nice, easy distribution. You all see this, class? It's a very easy distribution. So you don't have to have the cumulative distribution function. This is an easy calculation in your calculators. You with me? You can see that the probability of R being between 0 and infinity is 1. Because as R goes to infinity, that goes to 0 and that goes to 1. You all follow me in this class? All right, so if you want a probability, and these are actually questions from targeting and stuff. I mean, I don't do any kind of targeting radar, just want to be clear about this, but this is the kind of thing. So what is the probability if we have something where we know sigma x equals sigma y equals 1, right? The means of these things are 0. The probability that R is less than 2. In other words, that if you sent a missile or a bullet or an arrow at the target, and that was the true statistics of it, what's the probability that it would be less than 2? Now think what I just put here, right? That's the probability of it being less than 2. Follow me? Can you all follow me? What would that be? Well, it's 1 minus e to the minus 2, or e to the minus squared, or 4 over 2, e to the minus 2 divided by sigma squared. And I made sigma 1, so it's e to the minus 2. 1 minus e to the minus 2 would be less than 2. Follow me? It's a big number, by the way. What's the probability is greater than that? 1 minus that. That's all this does. And it's easy to do. With me? Now, something to be said about this, the mean value of this function f of R, and I'll be done here. If I take a look at R, the expected value, this is one I would have you work plenty of problems to make sure this is true. It's going to be the square root of pi over 2, and then it's times sigma of x. It's not the standard deviation associated with R. It's the standard deviation associated with either the x or y variation. This is important. And the last thing is the variance of R. Now this is where it gets a little different. When I take a look at the variance of R, remember to do that, I have to take this function, I have to multiply by R. So I get an R cubed here. Y'all follow me? And then I'd have to integrate, and it would be e to the minus R squared over 2 sigma squared. I'd have to integrate that from 0 to infinity. But at the end of the day, when you do it, you get this value. It's kind of nice. This is going to be 2, and it's sigma x squared. And then it's going to be simply minus this squared, or minus pi over 2 sigma x squared. And you can pull out the sigma x squared, but that's what the variance is. And it comes down to be about 0.429 sigma x squared. 0.429 sigma x squared. That's what, so that sigma x is the sigma associated with the Gaussian variables. I'm going to give you some problems with this, and I've got to give you your quiz. I'll give you time to complete it. So, why don't you do me a favor? How about, let's see, you guys move to the new state. You can fill this row up. You move up here. All right, I'm filling up the middle row. And then fill up the last row over here. So, I'm just trying to, and then let me get